Okay. A black one. Let's see what we're doing. Acids and bases. Exam 5 coming up on the 28th of October. And I'll ask if you have any questions that we need to deal with before I start talking. If not, we can just jump right into, for this review, we've got 2 review documents, one chapter 14, one chapter 15. So chapter 14 will be acids and bases in general and equilibrium. And then chapter 15 gets into more buffers. So let's see what we can come up with here. Well, let's cover the basics first. My mind's gone blank. That's what I get for doing 101 and 102 on the same day. Remember the Arrhenius definition of an acid produces protons, and a base produces hydroxyls, and these are both from the molecule. In other words, the molecule has to have one of these or one of those in its structure to be considered an Arrhenius acid or base. Bronsted and Lowry noticed that sometimes you particularly get basic solutions when there appears to be protons in the structure, but they don't produce an acid, they produce a base instead. So their definition says that an acid is a proton donor, and a base is a proton acceptor. Okay, so that way, their definition works for 99% of acids and bases, not just in aqueous solutions, but in non-aqueous solutions as well. But our principal interest is in aqueous solutions. Okay. So that being said, what happens with an acid when we put it in water? Say there's our generic acid with the proton available for donation, and in water, it's going to interact with the water molecule and transfer that proton to this water molecule, which leaves us with the, this is the acid, makes this the conjugate base. And then the water picks up the proton, it makes the hydronium atom. So that makes this the base as the acceptor, and this is the conjugate acid. Okay? Now that's what happens to an acid when we put it in water. If we use a base, Well, most bases are those with hydroxyls in them. But this doesn't have to be. It could be something like ammonia. Ammonia is still a base, and it can accept a proton, right? Bases are proton acceptors. But for argument's sake, we're going to put a base in water. So now the water becomes an acid because it's a proton donor. And then a proton donor, if a proton goes from here, it combines with the hydroxyls. To make more water plus that hydroxyl. A better example would be what happens to ammonia when we put it in water. So there's your base, there's your acid, and then the base, the proton acceptor, again, becomes the positive ion, and then that makes hydroxyl. Okay, let's see if we need any more definitions. Well, if that should be enough to get started. Okay, so we can write an equilibrium, right? I wrote the double barbed arrow in here, equilibrium for this acid. Now, if it's a strong acid, what happens? It just goes all the way to one side. Right? But for a weak acid, you have an equilibrium established, and the K for that equilibrium, Ka actually, is the conjugate base concentration there, A, and then in the denominator, you have the undissociated acid. And sometimes you'll see this as rather just a proton. They mean the same thing, and they give you the same results. Let's see, I think I got, yeah, I got something for Okay, so that's a Ka for the acid. We'll talk about Kb's in a minute. Well, we can do it now. So what will be the Kb for this first reaction? The Kb actually takes this proton acceptor and reacts it with water. Okay? So what happens then, it takes a proton and leaves a hydroxyl. So in that case, the Kb equals the conjugate acid, the hydroxyl, divided by the base. Okay, so these two are related, but they're not reciprocals of one another. What we have is a situation where, remember, this reaction is always taking place in water. That. And its Kw, the special case, is just this one, concentration times this one, and that's equal to 1 times 10 to the minus 14. Okay? So notice what happens. If we break this out into what is this equal to and what's that equal to, we find that we solve for this one, for Ka, then we find the hydronium equals Ka times Ha divided by A minus. Okay. And this one, we have the OH equals Kb times A minus divided by Ha. Okay. And if we substitute each one of these in here, notice that, let me get some more room on the board here. If we substitute this one in here and this one in here, then that's equal to Ka times Ha over A minus, okay? And then this one in here, Kb, try that again. Let's do this over again. Kb times A minus over Ha. Then notice that these cancel, those cancel, and Kw equals Ka times Kb. So if you have a Ka for an acid and you want to know the Kb for its conjugate base, here, the A minus, then all you need to do is divide Kw by Ka, and that'll give you Kb. Okay? If you need the Kb, how do you know you need the Kb? If you have the conjugate base of a weak acid reacting with water, then you know you need the Kb. And what it does is it leaves you with a hydroxyl on the product side. Those are clues that you need a Kb for that reaction. Okay? So that's a lot of theory, a lot of manipulation. We probably ought to get down to do some problems, I was thinking. That was just to get warmed up. So while we're on that topic, let's take an example. A real example. Not necessarily a problem that's in there. Let's take acetic acid. Okay? So acetic acid reacts with water to yield acetate plus the hydronium. So the Ka for this is going to be the acetate. And I'm going to stick the hydrogen in here instead of the hydronium, because the water is going to drop out anyway. Okay, and we know this value to be 1.8 times 10 to the minus 5. That's the one you're going to prove today. But what if we put this in water? Right, we start with pure water and we add the acetate ion in water. How does it react with water? Well, it's a very good proton acceptor. Why? Because it's a weak acid, right? Weak acid makes a strong base. So this strong base really wants a hydrogen, a proton. So it's going to take it from the water, and it's going to give you the acid, C2H3O2 plus hydroxyl. And the Kb is going to be equal to the hydroxyl and the undissociated acid divided by the acetate ion. Right. So that's a real world case where you're going to need Kb if you're studying this reaction right here. And then to get this value, you would say Kb equals Kw, which is 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And let's see, where's my calculator? It's over here. And I get 5.6 times 10 to the minus 10 would be the equilibrium constant for this reaction, the basic reaction of the acetate ion. Okay? Now, how do we get that in solution without having to put the hydrogen in there with it? You start with the salt, right? For instance, just the sodium salt of the acetate, sodium acetate, will give you this ion added to water without the hydrogen ion. And sodium's not going to react with water. Sodium likes it just fine the way it is because it's already an ion. It's just going to go in solution and be a spectator. One more example. Suppose when we react ammonia with water, we get the ammonium ion. Right? That's our conjugate acid. So in that case, we would have a Kb for the ammonia, 3. Right. So that gives us a Kb because we have the hydroxyl here and we have the hydrogen acceptor here. And the acceptor is a base. Right. So that has to be a Kb. And the expression would be okay, and no water because water is pure. Now, let's suppose we put the ammonium ion in water. These are two different situations. We're starting with this one now, putting it in water. This becomes the acid, this is the base. So now we get this one plus this one. Okay. So now, this being the acid, we need a Ka. So the Ka for this one would be ammonia, and then the hydronium, which I'm representing as a proton, and then the ammonium. Okay. Now I don't know what the Kb is or the Ka, but you would use the same process. If you know this one, then you divide it into the Kw for water, and you get the Ka for this reaction. Okay, so it works either way. Now then the question becomes, how do we get ammonium ion in solution without introducing an anion? that would compete with it? Well, you need the anion from a strong acid. So it would be either chloride or nitrate. Those would be my first two choices. So ammonium nitrate or ammonium chloride would give you this one without the interference of these spectators, because they're not going to react with water. Right? Remember, hydrochloric acid in water completely dissociates and chlorine doesn't go backwards. Same thing with nitrate. So that means you're safe putting these in water and getting no reaction with water. This is the only part of the molecule that will react with water. So these as your anions would give you this in water and that reaction. Okay, now perhaps we ought to get to some real problems. In the interim, have you thought of any that have been bothering you? Of that group that we had, chapter 14, we'll do that one first. We'll start off with chapter 14. And see if any of these give you trouble. Okay, I'll start. Number 1, which of the following is a conjugate acid-base pair? D and E is more than one. So let's see if there's only one or more than one. How about this one? HCl and OCl minus. So when they say acid-base pair, that means that's the acid, this is the conjugate base. Okay. Well, what is the conjugate base of this one? If you put it in water, you get this one plus this one, right? So what's the acid conjugate base pair in that reaction? It's HCl and Cl minus, not OCl minus, right? So that can't be it. Another thing that this doesn't, well, let me see. Maybe I'll get to one. Yeah, the next one is a good example of my next point. So is this a conjugate acid-base pair? Well, you look at the acid and react it with water. And what is it about acids and bases when they react? One proton at a time. So one proton gives you this hydronium. And what's left over? HSO4 minus. This one's missing 2 protons. That's not an acid-base pair. Acid conjugate base pair. Okay? How about C? Ammonium and ammonia. So when you put that in water, what happens? I think we just drew this one, didn't we? So we lose a proton from our acid to make a conjugate base, and it ends up on the hydrogen. Is that an acid-base pair? Yep. Lost only 1 proton and left us with the conjugate base here. That's 1. Now, if D's a good one, then E's the answer. But if D's not, so let's try this one. So what would that have to do? If we put this one in water, it's going to transfer that proton to that water. So this is the acid, this is the base in this reaction. So that proton transfers over, leaves us with this one and that one. So this is the conjugate base and this is the conjugate acid. So H3O plus and OH minus. Nope. How many protons had to leave this one to make that one? 2. Right? And you can only do 1 proton at a time. So that one is not. And that means E is also wrong, because there's only one that satisfies, and that's this one, C. Okay? Oops, don't want to erase that. We're still in chapter 14. All right, let's see. Oh, two's a good one. Which one of these reactions, hydrogen sulfate or bisulfate, which is another name for hydrogen sulfate, can act as either an acid or a base in water solution? In which of the following equations does HSO4 act as an acid? All right. So what does it take to be an acid? Bronsted-Lauer says you have to donate a proton. So this one has to donate a proton to that one. That makes this an acid. This is the base. This becomes the conjugate base of the bisulfate ion, and this is the conjugate acid. Right. So based on the definition, that's the one we're looking for. So let's see, which one is it? Well, let's see, which ones have water in them for the reaction? A and D. But which ones gives us the right results? Well, in A, water is the acid because it donates a proton and makes sulfuric plus OH minus. So the only one that fits is D. Right? Okay. Okay. Let's go ahead and do 3. As long as we got different topics, I'll just take it down the numbers. Which of the following is the equilibrium constant expression for the dissociation of weak acid, HOCl3? HOCl. What is that anyway? That's a polyatomic ion, hypochlorite. And ites become uses. So the acid would be hypochlorous acid. Dissociation of the weak acid. Okay, we're going to leave out the water for this one. So what it does is it makes this one plus this one. That means the K is that one, that one divided by this one. So that means A is the best answer for that. Okay. Notice all I did here was I just left water out. I didn't put water in on this side or water in here combined with the hydrogen to make the hydronium. That's why it looks that way instead of what you would expect with the hydronium ion in it. Let's see. All right, let's just finish out page 1 with number 4. Which of the following is not true for a solution at 25 degrees that has a hydroxide concentration of 2.5? So this is what we're given. 2.5 times 10 to the minus 6 molar. First one, is this true? Yep. KW. That's the equilibrium expression for water. Right? That's true. Doesn't have anything to do with this, does it? It's just asking, is it true? It's true no matter what you put in solution, in the aqueous solution. That's always operating. You always have that one operating. It's just that sometimes other reactions dominate. Right? Since this is 10 to the minus 14, then the equilibrium is pretty much pure water. So even though you have this in solution, this still works. It has to be obeyed because that's a constant. The solution is acidic. Acidic? Well, let's see. How do we know? Well, we need to find out what the pH is, don't we? All right, so what's the easiest way to find the pH in this one? Take the negative log of this concentration equals the pOH. Right, so 2.5 exponent 6 minus. Let's take the log and reverse the sign to be 5.6. That's the pOH. So what's the pH? 14 minus 5.6, which is equal to 8.4, right? So it's not acidic, it's basic, which is C, I think.
Yes.
So C is basic. That's true. But we're looking for the false one, aren't we?
Yes.
So we found it. What about D? The hydrogen ion concentration equals 4.0 times 10 to the minus 9. Well, we can do this two different ways. We can use an equilibrium expression for this based on hydrogen ions times hydroxyls equals 10 to the minus 14, right? Which means we have this one and this one, right? Just solve for hydrogen. Or we can take the anti-log of that value. So if we do it this way, then we would say 1 exponent 4 and then 2.5 exponent 6 divide. And that's 4 times 10 to the minus 9. All right, so that checks. But what if we do the anti-log of this one? So the anti-log of negative 8.4 equals what? That's 10x. Let's round it off times 10 to the minus 9. So either way works. So that was true. How about E? KW is independent of what the solution contains. Yep. That's basically saying KW is a constant. Doesn't matter what you put in it. KW is always there. All right, that was page 1. And I'm sure we're not going to have enough time to go through all the pages like that. So let's start cherry picking and get stuff that is likely to make a useful point. About 8. Which of the following solutions contains the strongest acid? So this is 5 molar HCl. And its Ka equals 6.2 times 10 to the minus 10th. B is 3.5 molar H2C2H6O6. I guess benzoic acid. So Ka1 equals 7.9 to the minus 5th. Ka2 equals 1.6 times 10 to the minus 12. Okay, why do we give 2 Ks for that one? Because they're 2 dissociable protons. C is 2.5 molar acetic acid. And we know the Ka of that one should be 1.8 times 10 minus 5. And then D, 4.0 molar HOCl, hypochlorous acid. Ka equals 3.5 times 10 to the minus 8. And then the last one, 1.0 molar HF with a Ka equal to 7.2 times 10 to the minus 4. Now, I spent all that time writing that up there, and actually, to answer the question, which contains the strongest acid, what's the definition of a strong acid? Well, a strong acid. All the protons dissociate. But relatively speaking, the stronger the acid, the higher the percentage of protons that leave the molecule to go into solution. Right? So how do we tell that? Well, let's use this one as an example. Oops. Hydrocyanic acid yields that plus that. Right? So we can look at each one of these as a proton dissociation. And that one's not going to matter. Remember, we determined during the lecture that the first one is the one that matters. We did it for phosphoric acid, right, for determining the pH. That one's the one that matters because it's so much bigger than that one, 7 orders of magnitude here. So we can ignore this one. So each proton that's given up shows us, based on the K, how far to the right it's going to go, right? So if it doesn't go very far to the right, that means this is going to be small and that's going to be large. And the K is going to have a small value. The smaller the value, the smaller this. The smaller the Ka, the smaller the dissociation, right? So that means the one with the biggest K is going to be the strongest acid, right? So which one's got the biggest K? That one right there. 10 to the minus 4th versus 8 minus 5 minus 5 minus 10. That just means it's going to dissociate the most, produce the most protons. And by our definition of strength of an acid, it doesn't matter what the concentration is. Strength of an acid refers only to the equilibrium constant. Right? That's an equilibrium question. I mean, that's a definition of acid strength. Now, if the question is which one has the lowest pH, that's another problem where you have to actually go in and do the calculations for each one
to find out what the pH is. Okay. But to answer this question, all we need to know is which one has the largest K value. Okay?
All right. Interrupt me anytime.
Sorry. I'll be working talking to them.
That's okay. If one of them just pops into your head, comes to mind, say you have a question about it, then we'll divert to that one.
Let's see. Here's a good one.
This is a hypothetical, number 12. So which one of these
These are diprotic acids.
A, B, C, D, just to show that they're different acids. And here are the Ks. Let's do it this way. Ka1 is here, and Ka2 is here for the second proton. Save us some writing. 4.2 times 10 to the minus 2. 4 times 10 to the minus 4. 1.3 times 10 to the minus 4. And 1.8 times 10 to the minus 3. Then the second dissociation, 1.8 times 10 to the minus 7. 6.1 times 10 to the minus 8. 5.2 times 10 to the minus 9. And 9.3 times 10 to the minus 4. Okay. Oh, and the last one is second Ka never affects pH. All right. So what do we need to know? We're talking about relative amounts. Does this one affect the pH of that acid? Does this one affect the pH? So forth and so on. The values here don't mean anything to answer this question. It's just how do these compare? Okay. So look at the difference between this K and that K. So this one is going to be HA minus yields A minus plus that one. And that's the second dissociation for that one. The difference in the equilibrium here is 10 to the minus 2 versus 10 to the minus 7. That's 10,000 times difference. This one is not going to affect the pH because it won't dissociate enough to overcome that any concentration there. So the difference, the spread between the two is what you're looking for, right? This is orders of magnitude difference. This one's 5, this one's 4, this one's 5, that one's 1. So which one's going to have an influence on the overall pH? That one right there. It will affect the pH. It won't affect it a lot, but it will be measurable. So it's the difference between the two that tells you whether the second one is going to influence. Okay? And of course, E is false. Well, E doesn't fit. D is the one. Because the second Ka does affect the pH sometimes. Not often, but whenever you find them that close, then you can expect the second one to be an influence on the pH.
Okay, that was, what was that? 12. Okay. Let's see. Let's see if this one will. Nah, let's skip that. That's not teaching as much. Let's get into some actual calculations. Or maybe we'll do rule of thumb first. Let's start with 16. So which of the following would give the highest pH, that is the most basic, when dissolved in water to form a 0.1 molar solution? 0.1 molar doesn't matter. It's just they're all going to form the same concentration. So A, strong acid, weak acid, potassium salt of a weak acid, potassium, weak acid, or potassium of a strong acid, or E, the ammonium of a strong acid. Okay. First of all, what's this one going to do? Well, they're all going to be the same concentration, 0.1 molar. Right? So what's the pH of this one going to be? Negative log of that one is going to be the negative log of 0.1 molar. So that one's going to be a pH of 1, 10 to the minus 1, negative log of 10 to the minus 1. Log of 10 to the minus 1 is negative 1 times a negative is a plus 1. So that's going to be pH 1. That's definitely out of running. It's not low enough. I mean, it's too low of a pH. The weak acid is still going to be an acid. And it's going to be greater than pH 1, but still less than pH 7. Okay. So it's still acidic. So we're looking at salts to figure out which one's which. So where does the potassium come from? Strong base, right? So what do we say when you combine a strong acid and a strong base, you get a neutral solution, right?
So this one, I'm jumping down to this one. pH is 7. It's going to be neutral. Strong acid, strong base. But this one, strong base, weak acid, is pH greater than 7. And how about this one? This one comes from a weak base, right? That's a weak base. Well, actually, that's not right. It comes from this one. That's the weak base that forms this acid. Yeah. The origin of this salt is from a weak base and a strong acid. So weak base, strong acid yields an acidic pH. Right? You guys just gonna sit there and laugh at me. So, which one has the highest pH? This one. That's the only one where the pH is greater than 7, because it's the product of strong base, weak acid. Strong base, weak acid means basic solution from the salt. Now, let's go down the line. 17 is the next one. Here we go. Select the answers that best describe an aqueous solution made from each of the following. Well, this is kind of a, okay, we'll just carry on. Sodium nitrate. We make a solution of sodium nitrate. Right? So where does it come from? This is a salt. This comes from a strong base. This comes from a strong acid, nitric acid, neutral. pH 7. Okay. 18. Sodium carbonate. Okay. This one comes from a strong base. That one comes from a weak acid. So pH is going to be greater than 7. Right, that's going to be basic. And in fact, it's got a common name called caustic soda. And it's caustic soda because it's very basic. You know, high enough concentration, it'll eat your hand off. It'll definitely show you where all your cuts are. So this one is C, answer. This one is B. 19, solid ammonium acetate. Okay. Ammonium acetate. We put it in solution, and we know that it originated from this one with a Ka of 5.6 times 10 to the minus 10, and acetic acid, well, they're giving us the Kb, so that's the Ka, right? Because this is the cation, so it's now an acid, right? So it's a Ka, and this one is the acetate ion. So we need to know the Kb of that one because it's going to interact with water and produce acetic acid plus OH.
So we need the KB for this one. We got to find out which one wins. 5.6 times 10 to the minus 10. Guess what? That one competes against that one. It's a tie. They're both the same number. All right, you put this in solution, that one reacts with water. Put this in solution, it reacts with water to the same extent that this one does. So this one is neutral. Okay? If this one were a larger number, say 10 to the minus 7 instead of 10 to the minus 10, that would mean that this reaction would win and produce more hydroxyls than this one would produce hydrogen ions. So that would make it basic. But if this one were larger, say 10 to the minus 3 versus 10 to the minus 10, it would be an acidic solution. That's that case where you couldn't use a rule of thumb. You have to know what their relative strengths are. That make sense? Think about it in a minute. Right, so what does this mean? The Ka for that means this one, that one yields this one, that one. So we're producing hydronium ions with this balance. This one, what are we producing? We're producing acetic acid plus hydroxyls. Okay. So if this one is large, a large number relative to that one, it's producing more of these. And this one is producing some of those, but less than those. That makes it basic. So that's why you need the Ka for this one and the Kb for that one to compare. You can't compare the Kas for each one because that one's the acid part and this one's the base part. So it has to be a Kb. Okay? I hope that explains it. Oh, number 20. Maybe this is an example where they're not equal. So let's look at 20. Ammonium perchlorate. Right. Ammonium perchlorate. And the Ka for that one is 5.6 times 10 minus 10. And the Kb for this one is 10 to the minus 21, roughly. Okay? So, which one wins? Kb is a lot smaller than the Ka, so the Ka wins and makes this an acidic solution. For similar reasons. This one reacts with water to produce hydrogen ions in large amounts relative to this one, which reacts with water to make hydroxyls in very, very small amounts. So the balance is toward the hydronium production, the proton production. Okay? Did I write that correctly? No, I didn't. There we go. Ammonium perchlorate. Okay? That's 20. Oops. Didn't mean to do that. See how we're doing on time. 2:15. got till 3:50 if we need it. Okay. How about this one? Which factor listed below is most important in determining the strength of an oxyacid? What's an oxyacid? Got oxygen in it. Now this one can be any number of oxygens. It could have 1, 2, 3, however many. So what's the most important factor in determining the strength of that acid? That right there. The number of oxygens. The more oxygens there are, the stronger the acid. And what was the sequence they gave us in our discussion earlier? On the slides, PowerPoint slides. Yeah, let's see. That's true. And then it goes. So each time you add an oxygen, you get a stronger acid. In fact, this one is by definition a strong acid. In other words, it completely dissociates in water. Whereas this one partially, this one less, and this one even less. That's all because of the extra oxygens. Increased strength this way. So that means the best answer is D for this one. The number of oxygen atoms present in the molecule. Okay? Okay, how about 24? Okay, question is, which of the species below, when dissolved in water, will not produce a basic solution? Will it either be neutral or acidic? So let's see, we've got this one and this one and this one. Barium oxide. Yep, that's correct. And this one, or none of these. And what are we looking for again? Not produce a basic solution. Not basic. Okay. So let me get my terminology correct. Remember, this one's an acidic oxide. How do we know? Acidic oxides are always oxides of nonmetals from over here. And when we react them with water, we get thank you.
1 sulfur, 3 oxygens, 2 hydrogens. And there's your acid. So that makes an acid solution. Okay. So that one's not basic. That's an acidic solution. What happens to this one? That's basic. Right? So that one's not basic. Satisfies the condition. That one is basic, so it doesn't work. This one is a basic oxide. And they're always formed from oxides of metals, particularly alkali metals and alkaline earths. So what happens when it goes into solution?
Yeah, I don't want to tell you wrong. Be sure I get this right.
Well, it'll take a hydrogen and also leave hydroxide. And then this can further dissociate. How about this one? That's just an Arrhenius base, right? So when it goes into solution, there's no ifs, ands, or buts about it. It produces a basic solution. So those are both basic. And then, of course, none doesn't work, because we did find one that produces an acidic solution, and that's the acidic oxide. Remember, all acidic oxides are produced by combination of a non-metal with oxygen. So what are some other examples? Well, carbon dioxide, right? Nitrogen dioxide would be a good one. I'm not sure about this one. I think, yeah, silicon dioxide, maybe even this one, P2O5. They should all be acidic solutions, form acidic solutions. Okay?
All right, what else on the agenda here? How about, what's this one? 31. Given the Ka for hypochlorous acid is 3.5 times 10 to the minus 8, Ka for HF 7.2 times 10 to the minus 4. Both at 25 degrees. Which of the following is true concerning K for the above reaction? Okay.
So here's our target reaction. We want to find out something about this reaction. Okay. So what's the K for this one? Well, let's see. We're given HOClKa. Okay. And that Ka is 3.5 times 10 to the minus 8. We're also given this one, HF. (7.2 times 10 to the minus 4). So can we combine these two and give us that reaction? Can we? Well, we can't add these two together right the way they are because HF needs to be on that side. Right? We need F minus over here and HF on that side. So what do we get when we put F minus on this side? Like that. Let's see. What would we normally do with a K value if you flip it? The K would be inverted, but we're in an aqueous solution. So this is actually not going to combine with H plus, it's going to combine with water. To produce HF plus OH minus. So if we combine these two, what do we get if we combine that one with this one? Okay, this one right, that's right, with water. I'm just thinking out loud here. On this side of the equation, now on that side of the equation, we get H plus O Cl minus, and then we're using this one plus HF plus OH minus. Right? Now, does that give us this one? Well, we've got this one and this one okay up there. We've got this one and this one okay up there. So what happens when we take water on this side and H plus and OH on that side, we get water again. So that one cancels, that one cancels, and that cancels. So we can use this equation. Why did I pick this equation? Because this one requires the calculation of Kb. We know that one like that. Right, so Kb is going to be, already got it here, 10 to the minus 11. Now that we got the Kb for that one, we got this one. So we combine the K's, right? What do we do to the K's when we combine equations? Multiply them? Is that right? Or do we add them? According to this, we add them. We add the K's. I'm not sure that's right. Equilibrium.
Nobody remembers? There we go. We add those equations together and multiply it. Yeah, that's what I thought. So what happens if we take this one and multiply it by by this one here? I may have figured that other one out wrong. Sign. And then times that one. I get the K for that reaction is 4.9 times 10 to the minus 19. Okay, the answer is still the same, but that's not the way you arrive at it. The value is Ka times Kb equals 4.9. I need to make that correction. In our worked problems, the answer is still B. The K is less than 1. But the K is not equal to this. The K is equal to that. Okay? See where I made my mistake in the worked problems? All right, that's 31. See if anything else we need, and I think there are some problems we need in chapter 14 that we haven't got to yet. Yes. All right. I'm going to do either 36 or 37. Let me see which one will take the most time. About 37. Okay. 37. What's the equilibrium concentration of H2PO4 minus in a 0.202 molar solution of H3PO4? All right, so we have, we're given 0.202 molar H3PO4. And what we want to know is, what's this concentration? Okay. So, what do we start out with? We start out with this one, 202 molar.
And how much of this do we have? 0. So which way is the equilibrium going to go? That way. So that means we're going to add some of that and an equal amount of that, because they come from the same place. We're only taking one off of there. We get that, and we lose some of that. So now the equilibrium expression is 0.202 minus x, and this is x, and this is x. All right. So we're given a k value. Yes, we're given a k value. Notice also that Ka1 is 10 to the minus 3, Ka2 is 10 to the minus 8. That's a 5 order of magnitude difference, so you can ignore the second one. And the third one also. Right? So we only have to concern ourselves with the first one. And that's equal to 7.5 times 10 to the minus 3. And that's equal to x times x, right? Products over minus x. Now, if we assume that x is going to be very small compared to 0.202, then we can work it out with x missing. But this 10 to the minus 3 tells me that x is probably going to be significant, particularly at that low concentration. So you're going to have to work it out with a quadratic. Or this is a weak acid. How about Henderson-Hasselbalch? I know that's in the next chapter, but would it work? So the pH is equal to the pKa plus the concentration of base and that's the log of the concentration of base divided by the log of the concentration of acid. Is that going to help us any though? We can, well, we don't know the pH. We know the pKa. That's the question. The concentration of this. So if we find out what the pH is, then we can take the negative, the anti-log of the negative, and they're both equal, so then we can find out this one. So if we found out what the pH is, we could do the rest. The problem is, this is an x, and this is a 0.202 minus x, right? We can't resolve that figure if we have x over 0.202 minus x. How do you resolve that before you take the log of it? Well, let's see. The log of that would be what? The log of x minus the log of 0.202 minus x. And we're still stuck. We don't know what x is. All right, so we do have to do this one. And I've already worked out the problem and found that making x disappear in this term does not meet the 5% rule. So we have to do the calculation. We have to say this times that, which would be, let's see, x squared on one side, and this times that on the other side. So it's this term times that term is 1.52 times 10 to the minus 3 minus x times this one. Right. I just left these over here and put these over there and then flipped them to make that. Now 0 equals, I'm going to move all these over here to give us this one positive. This one also positive. This is moving to the other side. This one moves to the other side as a negative. There's your quadratic. Then you just need to solve for x, which is minus b, this term right here, plus or minus square root of b squared, which is this one, minus 4 times this one, which is 1, and c, which is this one, minus 1.52 times 10 to the minus 3, there. And then all over 2 times a, which is 1. So I didn't write this one out, but you put that one in there, and that one in there. And then you resolve this term, and then you say, what is it plus? What is it minus? And these are our choices. X is either equal to 3.54 times 10 to the minus 2 molar, or minus 4.29 times 10 to the minus 2. You can't have a negative molar, right? So this is our molarity for H2PO4.
Let's see. Let's move on to chapter 15, before we run out of time. Okay.
Fix this. Erase that too. Let's move to the next chapter.
Now, let's see. Chapter 15, we're looking at acid-base equilibrium and buffers. So we're going to get a little bit more involved with the equilibrium question. Let's see, quarter 3. About an hour before we have to go to the lab. Let's see. How about scratching my head, wasting time. about number 2? Trying to decide which one of these
Would make an effective buffer. So A is a mixture of 100 milliliters of 0.1 molar hydrochloric acid and 100 milliliters of 0.1 molar sodium hydroxide. Would that make a buffer? What do you get when you add a strong acid to a strong base?
You get a neutral solution.
This acid is completely dissociated. Sodium hydroxide, completely dissociated. There's nothing in there that will pick up protons if you add them, or hydroxyls if you add them. Right? So that's not a buffer. Strong acid, strong base is not a buffer. How about this one? The 100 milliliters of 0.1 molar ammonia, and it gives it a K value. Kb equals 1.8 times 10 to the minus 5. Okay, and then we're going to add that to 100 milliliters of 0.1 molar sodium hydroxide. So what do we have? You have a strong base, okay? So if you're going to mix a strong base with something to make a buffer, it's got to be with a weak acid. You can't mix two bases and get a buffer. So ammonia is a base, right? Because it goes like this. Like that. That's your Kb. Kb is predominantly over here. Right? This is your predominant species. And that one just makes a bunch of hydroxyls. So if it's already basic, and it will be basic because 10 to the minus 5, 10 to the minus 5 is as opposed to what other reaction in water? Kw, 10 to the minus 14. So this reaction is going to control that one right there. So that means it's already producing some hydroxyls and you're going to add more hydroxyls. That can't be a buffer. Okay. How about, oh, C. Did I skip one? No, I didn't. C. Oh, C is 100 milliliters of 0.1 molar hydrochloric acid plus 100 milliliters of 0.1 molar ammonia. And again, the Kb here is 1.8 times 10 to the minus 5. Okay, so now we need to see
a weak base and a strong acid. There's potential for buffering there. As long as one of them is weak. One of them, if the base is weak, then the acid needs to be strong. So we have potential. So what we need to do is say, are we in the buffer zone? Right? So how much ammonia do we have here? How many moles of ammonia? 0.1 molar times 100 is 10 millimoles of ammonia. And this one is, what, 10 millimoles? Yeah, 10 millimoles of protons. So what have we done? We've taken this and this. We're not in the buffer zone. We've reached equivalence. We've added enough acid to entirely consume all of our base. Right? So that can't be in the buffer zone. Remember our titration? Well, in this case, you start with the base. We're going to add acid. It's going to start here and go like that, and then like that. So we're not in the buffer zone here. We're actually right there at the equivalence point. So that's why C is not a buffer. Okay? How about D? Kind of running out of options. D better be the right one. So what do we have for D? 2D. We have 50 milliliters of 0.1 molar HCl plus 100 milliliters of 0.1 molar ammonia. Okay. So, let's see, the way I worked it out, I actually calculated what the pH is. But to answer the question, which of the following mixtures would be a buffer, all we need to do is say, all right, what do we need to know about the buffer? We need to know the ratio of the conjugate base to the acid. Right, so for this one, we have 5 millimoles of HCl, and this one we have 10 millimoles of NH3. So what we've done is we've consumed half of these, and now we have, we've added protons to this one, right, from here to only half of them. So now we still have this much ammonia left, and we have this much of conjugate acid, right? So this one goes in here. This one goes in here because it's the acid part. What's that ratio? 1:1. Remember what we said about the Henderson-Hasselbalch equation? The ratio of the acid to the conjugate base, if it's 1:1, you're right smack dab in the middle of your buffer zone, right here. That's 1:1. That's ideal. Okay? So this one is definitely a buffer. Now, the way I work the problem out here in the work problems, I actually tell you what pH that occurs. What is this pH? Well, it's 9.2 something. But we didn't need to know that to answer the question. I just did that for kicks. Okay? Now, what can be a buffer and what can't be a buffer? Most buffers are weak acids with a strong base. Right? But there are some of them, like this one, this example, where you have a weak base and a strong acid. But you end up with the same situation. What happens if we add protons, right? If we add acid to this one, what's it going to do? Well, if we add more protons, it's going to shift over to a little more of this. If we add hydroxyls, it's going to take protons from that and shift over here. But the overall ratio is going to be well within the buffer range, as long as we don't add too much. Okay. What shall we do next? Let's see. Make sure I cover all our topics. Can you derive the Henderson-Hasselbalch equation?
Suppose I put that on there and said, as a short answer, derive the Henderson-Hasselbalch. And let's just assume that in its derivation, in fact, the original derivation by Henderson and Hasselbalch, actually Henderson first, Hasselbalch modified it, is you start off with a generic weak acid. Okay. It produces that and that. And this weak acid has a Ka of some value, whatever.
Okay, now can you derive the Henderson-Hasselbalch from that?
Well, let's see. The Ka expression is going to be what? This one divided by this one. Okay?
Once you get to this point, that's where you start deriving the equation. Because this is an equation. That's not, that's a reaction. This is the equation. So what do you do first? Take the negative log.
Take the negative log of the entire thing. So what's the negative log of Ka? pKa, right? What's the negative log of H plus? pH. Now, I jumped ahead. Hold on a second. Let's do this. Let's solve for hydrogen ions first. Okay. Keep hydrogen here. That means Ka times Ha divided by A minus. There we go. So I just took this portion right here, brought it across, which flipped it over, and there you have that expression. Now take the negative log of the whole thing. Negative log of this one is pH, right? Negative log of this one is pKa. And when you take the log of a product, the log then is, the log expression is an addition. So the log of this one is plus the log of that one. So the negative log of pKa is this one, but then the negative log of this expression there. Okay? We can't resolve this one into a simple expression because we don't know what HA and A minus are. So we have to leave it like that. But we don't like negatives in our expression. So how do we get that to become a positive? Well, the negative, the log of a quotient, like this, if you flip the quotient, then it becomes the positive log of that one. Plus, now we put the conjugate base on top and the acid on the bottom. So this requires that you know how to manipulate logs. But that's the derivation of the Henderson-Hasselbalch equation. And these values, in order to use this equation, we need to know what the equilibrium concentrations are, right? Square brackets. You know what the equilibrium concentrations are and the pK, then you can find out what the pH is of that solution. If we don't know what the equilibrium state is, what do? Well, you set up what's the controlling reaction, then you set up an ice table and find out what the equilibrium concentrations are. Then you can plug it into your Henderson-Hasselbalch. Let's see if we can find one of those. Let's see here. We'll do these before we get to indicators. That's a step beyond what we're doing. How about here's a nice one. Let's see. Which way did it go? 23, chapter 15. Here we go. So let's see if we can, this was kind of involved. So we need to take it logically. We need to say, all right, what do we know? Well, we're given 50 milliliters of 0.0350 molar hydrocyanic acid with a Ka of 6.2 times 10 to the minus 10. Okay? And we're going to titrate it with 0.0333 molar sodium hydroxide solution. That's not hydrochloric, it's hydrocyanic. There we go. if we add $15 milliliters, this is the titrant terminology. That's the titrant. This is the weak acid titrated with a strong base. We want to know what's the pH. Question is, tell us the pH of that solution. Okay. So, step one. This is one of those problems where you break it into two different problems. The first one is the stoichiometry. That is, you let the reaction of this acid and this base go to completion. Then you take the results of that reaction and find out which is the controlling reaction. Well, this is a strong base, so this is the only thing that's left. That's the controlling reaction. So we have, before the reaction, how many millimoles of HCN do we have? So this is before. HCN and sodium hydroxide. So how many millimoles of each one do you have? 50 times 0.035. That's 1.75 millimoles, right? Sodium hydroxide is 15 times 0.033, and this is 0.4995 millimoles. So what happens when you let them go react to completion? What happens? If we let all of this one react with that one, which one's excess and which one's limiting? Sodium hydroxide is limiting, it runs out. So after, you end up with that much plus minus 0.4995. You have this much HCN left over, 1.25 millimoles. Okay? So now we have a place where we can start our equilibrium. And here's the equation that governs the equilibrium, HCN, because now we're saying there's no sodium hydroxide left, right? So now the controlling reaction is HCN yields H plus CN minus. Okay? So initially, now that we have this set up here, initially, we have how much HCN? 1.25 millimoles. Remember, we're working in concentrations. So it's 1.25 millimoles for how many milliliters? 65. 65 milliliters. And that's equal to 1.92 times 10 to the minus 2 molar. Okay? How much CN minus do you have? Well, what's left over? CN minus. Oh, okay, I forgot to make that point. If this is HCN, and we combine OH with this one, what does that get us? CN minus plus water, right? OH combines with H to make water and leaves us with CN. So how much did we use up? We had 0.4995 millimoles used up. That means that this is 0.4995 millimoles divided by 65 milliliters. Okay? So that concentration is 7.68 times 10 to the minus 3 molar. And how much hydrogen ion do we have? Well, this is initial. We have 0. So what's the change? Which direction is it going? I'll take a wild guess. If there's no hydrogen, which direction is it going? That way. Right? It's going to make some hydrogen. So we're going to subtract some of this. We're going to add an equal amount of this and add an equal amount of that. So the equilibrium then is, this is X. This is 7.68 times 10 to the minus 3 plus X. And this is 1.92 times 10 to the minus 2 minus X. Okay, so now what you have to do is go to this expression where K equals this one times this one divided by this one. Plug in your values. We have the K for that one here. Plug in these values. And then decide if we're going to be able to use the, let's see, our concentration, starting concentration is pretty low as compared to this. It might work as an estimate. We can try it. What if we do that? So what's our expression going to be now? K is 6.2 times 10 to the minus 10. Hydrogen ions are X. Cn minus ions are 7.68 times 10 to the minus 3 plus X. And then 1.92 times 10 to the minus 11. Wait a minute. No, minus 2. And that's minus X. Okay, so can we say that X is so small that we can ignore these? Well, I kind of doubt it. We're probably better off using the quadratic. So the quadratic solution gives us two values. One is negative, one is positive. The positive one is this one. The other root's negative. So then X is equal to hydrogen ion concentration. We just take the negative log of X, and that's equal to 8.81 pH. Now, I wonder if Henderson-Hasselbalch would work with this one. If we say, what's the pH? The pKa is the negative log of this value, negative log of 6.2 times 10 to the minus 10, plus the log of the conjugate base, which is this one, over the conjugate acid,
and then -2. Now let's see if it works. Calculator. Go on time. So 6.2 log. This is 9.21, and then whatever this is, 7.68. 2. Log. This is minus 0.38. So let's see, 0.38, enter, 9.21. 8.8. Sure will. Once we get to this point, we establish that as our acid. This is our conjugate base. Plug those values into Henderson-Hasselbalch, and you get your pH. So we can avoid quadratic solution. Okay? A lot quicker. And you don't have to deal with quadratics. Okay, let's see. 3:15. That means 35 minutes. Yep, 35 minutes. We need to talk about indicators. All right. Talk about indicators. How do we know when to use an indicator and which one works best? How about this one? Let's see, where is it? Do this one and one other one. $19. Okay, 19 in your problem set requires that you calculate the pH at equivalence for each one of these. That on a test would just take entirely too much time. That would be the whole test by itself. So suppose I give you this question, and I tell you what the pHs are at equivalence. Does that help you? What's the purpose of an indicator anyway? No idea? Just to make pretty colors? The purpose of an indicator is to tell you when you've reached the equivalence point. All right, and so the equivalence point is a particular pH. And if you've got an indicator that'll change color at that pH, you've got a good indicator. Right? So with that being said, suppose we have these choices. F19. So we have methyl orange, methyl red, bromothymol blue, phenolphthalein, phenolphthalein, and alizarin yellow. The pH, the range in which these pH indicators operate, pH range, this one is 3.2 to 4.4. This one is 4.8 to 6. This one is 6, 7.6. This one's 8.2 to 10. And this one is 10.1 to 12. All right. Suppose you have the equivalence of your reaction. I'm just going to give it to you. The equivalence of your reaction, you have these choices. And E. This reaction, the equivalence is at pH 7. This one is equivalence at 2.94. This one at 4.63. This one at 7.92. And this one at 8.72. Now the question is, which of the following reactions would methyl red be the best choice? Well, look for ones that are within that range first. Right? That's outside, that's high, high, low. Well, that's right, that's too high, right? High, low, high, high. Right, so the nearest one is this one. Will it work? Well, the fact of the matter is, when you have a titration, you want to get as close as possible. And if your pH, if your hydrogen ion difference is pKa plus or minus 1 unit, you're in a good range. Now that's the buffer range, excuse me. The equivalence range puts this one at 4.63. So the nearest one, because these are so far away, the nearest one for methyl red is that one. Now, should we be concerned that the equivalence point is outside the range? No. Why? Because the change is going to take place at 4.8 and only get stronger towards 6.0. So what we're saying is that, well, what's the other color? We're not told what the colors are. Well, that's the best one for this reaction. Why not the others? Well, the others, these haven't been chosen. So it's got to be one of these others, right? This is too low, much too low. This is much too high. It's almost 2 units high. And this is almost 3 units high. So this is really the closest one for methyl red. Now, could we pick a different indicator that would be better? Oh, yeah. These are the ones we were given. So we're saying, what's the best one? But if you can find an indicator that puts 4.63 in the range, it would be better. I'm just looking to see. No, we don't have it. Any questions? All right, I have one more issue that I want to hammer. Let's see, where is it? Here it is. It's not in the review. All right, I'm gonna have to make this one up on the fly. All right, so this one's not available in the review. That's something I need to correct. But suppose we have a titration curve. So we're starting out with an acid. That means the pH is going to be, let's see, 2, 4, 6, 8, 10, 12, 14. And let's say this is 2. We're going by units of 2. Okay. And we've got a starting point right here. Right? And then it goes up to about here, about right in there. And then goes up, that, and then we've got, this one goes up towards just under 10, and then on up toward 12, and then it goes up like that, and then it goes up like this. Okay. There we go. So we've got these positions marked. This one's A, this one's B, this one's C, this one's D, this one's E. And this is the amount of base added. Okay? So what's the pH at the first equivalence point? Where are our equivalence points? Where's the first equivalence point? Right there. At that point, the amount of acid is equal to the amount of base for the first proton. Okay? So that means the first equivalence point is pH 6. What would be the second equivalence point? pH. Well, roughly 12. Right? So the second proton that we take off the acid, because this tells you that you can have a diprotic acid. Because there's one equivalence, there's the second equivalence. Right? This could be it could be sulfuric. All right? So that amount of base is required to remove the second proton. Where are the buffer zones for this acid? It has 2, doesn't it? One of them is right here, around B. The second one is right here, around D. Approximately pH 10 is one buffer zone here. The other buffer zone is about 2.5 pH. Okay? So which would be the best buffer zone to use for this acid? Take your pick. Either one would work. Either the pH 2.5 or pH 10. All you have to do is add base until you get to that range, then you've got your buffer. And it's in that zone. And it'll hold close to pH 10 as long as you're within that range. All right? Well, I don't know what else to say. That beat a dead horse. Okay, so we want to talk about the lab a little bit. I'm sure everybody's prepared for it.
Do you have an extra copy of it? I ran out of paper, so I could probably from last night.
Oh, I didn't send a copy home with you?
You did, I can't find it.
Okay. I just haven't got an extra copy.
I don't get a lot of my stuff. She had 3 bills and I think.
Oh. Mm-hmm.
I think she was mad that there was stuff on the counter she wasn't supposed to touch.
The dog ate my homework.
Written, I'm thinking that she's just got separation anxiety, because it's like, she doesn't do that stuff around there, so they think that I'll leave.
Uh-huh. Okay. All right, let me get, where's my, here it is. So we're gonna be doing Ka acetic acid, which means we're gonna take a solution, make a solution of acetic acid. Well, actually, it's already made up. And then in our burette, you remember the long skinny thing with a stopcock? We're gonna put base in that. And then we're gonna measure the pH. So we're gonna put in a little, we're gonna measure the pH at the beginning. And we're gonna put in a little bit of base according to the instructions. And measure the pH again. And we're gonna record those. Added base. 0 added base, this pH. So many mils of base, this pH. And just keep going, and the pH is gradually going to increase. Then we'll plot it. Get this out of here. This one. Okay. And let's erase this. I'm just going to let this thing keep recording. Okay. Does everybody remember how to use a volumetric pipette?
Yes.
With the bulb and all that stuff? Okay. We won't have to go over that. All right. So you're going to have your data. It's going to be pH versus added base. So for 0 added base, you're going to get a pH somewhere in the neighborhood of like maybe 2.5, something like that. And then as you add base, your pH is going to increase, like 3, 4, something, all like that. So you get that data set. Then you plot it. So this is added base. And this is your pH. And your pH is probably going to be in the neighborhood of around 2. Right? And it's going to go up quick to begin with, and then it's going to flatten out. off any more than that. Right? So your pH is going to start off increasing fast, and then it's going to slow down. And you're going to get this part of your curve. That's the buffer region right here, because the pH is not changing much. And then once you've exceeded your buffer, it's going to go like that. Flatten out at the top. Okay? This is going to be in milliliters. And what you're going to have here is your equivalence point. So at this point, and we don't need an indicator because we have a pH meter. Okay. So we're going to know exactly how much base, however much base it takes to reach the equivalence point. So where is the middle of the buffer range? 1/2 of that value. 1/2 of the amount of base added gives you the middle of the buffer range. Okay, so how do I know that? Well, you'll see it, but I know it because of Henderson-Hasselbalch. Oops. Okay. I know the best buffer range is where this one is equal to that one. Okay. So if I start off with this much and I add base to it, and we end up with water plus this one, okay? Then at what point does this one equal that one? If you start off with this one, right, so much of that one, and this one is 0, then when are they equal? When you've used up half of this one, right? If you use up half of this one, minus 1/2 x, and that gives you a plus 1/2 x over here, then this makes 1/2 of your x here, 1/2 of your x there. Now they're equal, right? So if these two are equal, then that's the middle of your buffer zone. So half of your original amount of acid used up puts you right here. And how do we know that? Well, we've got this much to reach the equivalent point. That's when you've used all of that up. So you only want to use up half of it. So if we use up half of it, that puts us back at half the amount of base added. Okay? So now, with half the amount of base added, so let's just say this is, for argument's sake, 20 mils. So this would be 10 mils. So at 10 mils, you go up here, that's the middle of your buffer zone. Okay? We're not finished yet, because the question is, what's the Ka of acetic acid? Well, look, Henderson-Hasselbalch again. If we're in that buffer zone where this is equal to that, what is this term equal to? If that's equal to that, that's 1, right? If that's equal to that, this term is equal to 1, and what's the log of 1? 0. 10 to the 0 power is 1. So that means this one drops out, and at that point, pH is equal to pKa. So you just have to read across here. That pH is pKa. Okay? And then all you have to do is take the anti-log of the negative.
So you say 10 to the negative pKa is equal to your Ka. Okay? That's it. Simple. Real simple. And you figure out what this is and compare it to, this is your accepted value. 1.8 times 10 to the minus 5 is the accepted Ka of acetic acid. And you compare yours to that one. And say, what's your percent error? That's basically it. And then there's some discussion questions in here. Pre-lab questions. Let's see. Am I expecting the pre-lab? Let me see. Wait a minute. Let me look at your copy, the student copy. Lab questions, yes, there they are.
Yeah, we have discussion questions, pre-lab questions, and lab questions.
Oh,
Are the pre-lab?
Pre-labs.
Yeah, there's, wait a minute.
There's 2 pre-labs,
Wait a minute. I
3
want
discussions.
Let me look at your copy because I want to see what you're responsible for. I want to grade you on something I didn't give you to do. That would not be fair. There's discussion questions, all right. I'm supposed to work these with you before class. Pre-lab, assign students. All right. Well, I can give you some hints. How about that? Oops, too many copies. All right, let's work pre-labs first. I'm gonna leave that there until I figure out what pre-labs. Pre-labs. Which way did it go? Let's discussion. Pre-lab. Okay. We can erase the left-hand side pretty easy without disturbing the rest of it, in case we need it. So these are the pre-labs. First one. Write the balanced molecular equation for the titration of acetic acid with sodium hydroxide. The molecular equation, right? So if you're starting out with acetic acid, you're going to react it with what? Sodium hydroxide, right? So these are the 2 reactants. There. This is the molecular equation. So we're not going to bust it up into pieces. We're just going to say what happens. Well, this one, the hydroxyl separates and combines with the hydrogen, right? Makes water. H2O. What's left over? Well, sodium then combines with acetate, right? Let's see, this is an aqueous solution. This is aqueous. That's pure liquid. And this is aqueous. So everything's soluble. It's just we represent the balanced equation as in molecular form, even though we know that they're really ions in solution. But the question was asking you for the molecular equation. Okay, any questions about that one? That's fairly simple. Whenever you're doing an acid-base titration, or any titration for that matter, you need a balanced equation to work from. You need to know what's going on in the solution. It's hard to see from there.
I don't have my contacts in there.
Oh, all right.
I was rushing out of the house.
Come on down. Which one is that? Wheel of Fortune?
Yeah.
Or is that Let's Make a Deal? Wheel of Fortune?
I think it's Wheel of Fortune.
Anything else, they want the same thing anyway.
Yeah, that's right. Okay, the second one,
The Ka of a formic acid, so here's formic acid. That's formic acid. Now, you don't need to know that to answer the question. The Ka is 1.8 times 10 to the minus 4 for formic acid. So actually, this is the proton that is released from formic acid right here. Not that one, this one. Just a point of information. The Ka of lactic acid, is, no, that's acetic acid. Lactic acid is, I think it's that one. But the Ka for lactic acid, let's see, this is formic acid, this is lactic acid. There we go, that makes it easier. The Ka for lactic acid is 1.4 times 10 to the minus 4. So they're pretty close. Which acid is stronger? Well, yep.
No, well,
The largest Ka, right? Remember what Ka means? It means one proton ends up on the product side along with the conjugate base. So the bigger this side means stronger, which means this value has to be larger. So the largest value is the stronger acid, right? Did you say formic?
Mhm.
Yeah, that's right.
okay.
That's right. So formic acid is the stronger. Now the next question is, what's the pKa of each acid? Well, we just take the negative log of each one. pKa here, pKa there. Let's see. This one turns out to be 3.74 for formic acid, and this one is 3.85. So the pKa's are like the pHs. The lower the number, the more acidic. So the pKa's, the lower the number, the stronger the acid. Right? So 3.74 is less than 3.85, makes this one stronger. It's a similar, really an artifact of the log transformation. Same as pH, right? Low pH is stronger acid. So low Ka is also stronger acid. Okay? Those are the pre-lab questions. Now, let's see. Laboratory questions. Define the following terms. Define the following terms. No, that's discussion questions. Lab questions are different.
We're on the very back page.
Very back page. There's discussion questions. Here we go. Discussion questions. Is that in your printed copy?
Yes.
All right. So this is really just the definitions. define these terms. So what's the equivalence point? That's the point in a titration where the moles of acid equals the moles of base.
This is at the point where they're equal.
They're exactly equal, yep. Oh, that was A. B is endpoint. What's the endpoint of a reaction? Of an acid-base titration. It's related to the equivalence point. The endpoint is an approximation of the equivalence point based on the color change of an indicator. Okay. How about Ka? What is Ka for your acid? It's the acid. It can either be protons or hydroniums, either one. Because these are the products, right? Products. And this is your undissociated acid. So that's what your Ka represents. It's the equilibrium constant for the dissociation of an acid. D, what is pKa equal to? It's simple. It's just a log transformation. It's a negative log of the Ka. That's it. Let's see. And there's two more. Discussion question 2. If you have 23.9 milliliters of sodium hydroxide solution, aqueous sodium hydroxide, and that much sodium hydroxide solution, and we don't know what the concentration is. Right. And we've got that titrated against 25 milliliters of 0.105 acetic acid. Let's see. What's my abbreviation for that? There. That's my abbreviation for acetic acid. Okay. Then the question is, what's the concentration of your sodium hydroxide? We did this before, didn't we? First semester. When we were standardizing our base to determine the molecular weight of citric acid. Yeah, we had to do this one. So what we're saying is the molarity of the base times the volume of the base is equal to the molarity of the acid times the volume of the acid. That's only if there's one hydroxyl and one acetate for each one. That works. If you used sulfuric acid here or a polyprotic, that wouldn't work. You would have to substitute instead normality here. Okay. But we can use this one because they're 1-to-1. Okay, so the molarity of the base is our unknown. The volume is 23.9 milliliters. And that's equal to the molarity here, 105 and 25. Okay? So if we solve that for the molarity of the base, we should get in the neighborhood of
0.110 molar. Okay. So what would we do
If we had a diprotic acid here, that's two, so two protons. Well, the normality of the base would be the same, right, because it's only got one. But here, the normality of this acid would be twice, right? Because the molarity of the acid produces, in the first case, one proton, but in the second case, two protons. So the normality would be twice that.
And then you could plug it into your expression. Hold on a second. Is that right? Let me see. Let's do that. That would be our diprotic acid. And if I said this was 0.1 molar, then it would produce 0.2 molar protons. Right, okay, so it's double the molarity. I'm just checking myself. The normality. Actually, that's the molarity of the acid. No, normality would be this. Normal. Why? Because this then would produce 0.1 molar hydrogen. Okay, I said that backwards. If this were diprotic, the normality would be half that. 0.0525. That works. That's why I didn't spend a whole lot of time on normality, because it's useful if you use it a lot in your work. But if you don't, you can get confused real fast. So the best rule to follow is, rather than use normality, write out your balanced equation. Then you can use molarity on the components and use your conversion, like 2 to 1, 3 to 1, to determine the values for each side. Okay, 3. In a titration of weak acid, the midpoint corresponds to a pH value of 6.1. The midpoint? Oh, okay, so the midpoint, what we're saying is the midpoint of the reaction is where half of the acid is neutralized. That's right in the middle of the buffer zone. And that pH, in this case, is 6.1. That's what they mean by midpoint. What are the pKa and the P and the Ka? Well, if that's the midpoint, then this is equal to the pKa. And the Ka is equal to 10 to the minus 6.1. Or the anti-log of minus 6.1, which is 8 times 10 to the minus 7. Okay? That one is a problem in wording. When it says, what does it mean by the midpoint? We've not used the midpoint as a descriptive term. So you have to understand what midpoint means. Midpoint just means right here. That's the whole point, that's the midpoint. And then the rest of it is simple. Okay? So did I leave any? Yeah, I did leave some laboratory questions that need to be answered on your own. Well, let's see. Should we be expecting negative?
She said she was on her way, she just stuck in traffic.
Okay.
She don't live too far away though, so she should.
Okay. So we'll take a short break, reconvene in the lab. And everything's either set up on the bench or is on the table or rolling tray. Let's stop this thing before we get